Welcome to Lecture 1 of Advanced Microeconomics with me, Dr. Craig Webb. In today's lecture, our big topic will be information. Indeed, information and how it affected economics when problems of information were taken seriously is going to be a big theme on this course. But today we're just going to introduce formally the idea of how we model information, what we mean by better information, by asymmetric information, and heterogeneous information. And once we've done that, we'll cover some basic elements of probability theory, conditional probabilities, and Bayesian updating. So lots to do today, so let's get started. Okay, so let's start by thinking about why information is such an interesting topic to study. Now, if we think about information as a good, I've listed here several properties of information. Some of these are shared by other goods, but I can't think of any other good that has all of these properties at the same time. Okay, so first of all, information can be privately known, it can be kept secret, and you could think of it as something that can be owned, so it can be sold as well. We could sell information. Also, when we sell it, we pass on the information, but we keep it at the same time. So just because I sell some information, I don't forget what I know. So there aren't many goods that you get to keep at the same time that you give them away. It's also basically free to give away or to reproduce. So when we think about pricing information later on, something like price equal to marginal cost is probably not going to capture very well what's going on as we give away information. Also information, it cannot easily be disposed of. So if I have a more tangible good, of course, I could just dispose of it and I don't have that good anymore. But once I've learned some information, I can't physically remove that part of the brain that is storing that information. So we basically assume that when you learn something, there's nothing you can do about it. You then have to carry on with that information forever. Also, we can't audit a person and detect what information they have. Okay, well, if they're just simply standing still, we have no idea what their information is. It might be possible, and this is going to be a big part of our later studies, it might be possible to detect what information a decision maker has by observing the decisions that they make. So somebody with certain information would act presumably in a different way to somebody else. And that's going to be important later on. Indeed, we're going to talk a lot about incentivizing people with certain information to behave in a certain way. Okay, and that's a very important idea in several of the later lectures. Also, information could clearly have different value for different decision makers. So, to give an extreme example, if somebody already knows the information that I have, then they would place zero value on that information if I tried to sell it to them. But also in general, the way we will value information is going to be based upon how useful it is for that specific decision maker with their specific preferences in order to help them make specific decisions. So it's going to depend on a lot of things, and it's going to have different value in all sorts of different circumstances. So what do we mean by information? We've talked about it intuitively, but we haven't really defined information. Now, in intuitive language, we think of information like facts or pieces of news. And in computer science, I'm sure there's a specific definition that relates to bits of data and so on. In microeconomics, we mean something quite specific. When we talk about information, we're going to mean that information is a reduction in uncertainty. Okay, so that's what we mean about information. There is uncertainty in the world, there is something that we don't know, and information will reduce that uncertainty. Of course, to model information, therefore, we're going to need to know a lot about how to model uncertainty, which we will cover next, and also how to quantify uncertainty using probabilities and so on, which we'll cover towards the end of the lecture. So let's talk about modeling uncertainty now, and we'll go on paper and outline the basic framework for modeling uncertainty in microeconomics. Okay, so let's talk about how we model uncertainty in microeconomics and in decision theory as well. So uncertainty, the most important idea we'll need today is the idea of a state of the world. States of the world. So what do we mean by these terms? Well, the world, in our case, is going to be the object that we are interested in knowing about. Okay, so it doesn't need to be the entire world or the entire universe. It might be, for instance, the outcome of rolling a dice. It might be the weather tomorrow. It might be the position of the stock market. So we first describe the world that we're interested in insofar as making our decisions involving uncertainty. So that's what we mean by the world. Now, the idea of a state is a complete description of the world, and it leaves no uncertainty. Okay? So, mathematically, we're going to write a set of states, and we'll just use capital S to be some set. Let's label the states in it S1 up to, let's say, Sn. So this state space, we call this a state space or a set of states, has n different states in it, n different ways of describing the world. Okay? Now, uncertainty exists in this case when we don't know the true state. Okay? So let me put this in large letters on the screen. If we know the state of the world, there is no uncertainty. Okay? So if we're able to fully describe the world in which we're interested in, insofar as our decision making is concerned, then we would say there is no uncertainty. Uncertainty exists because we don't know the state of the world, or we may not know the state of the world. Okay? Now, it might be that the state of the world is something that would be decided in the future, so I might be talking about tomorrow's weather. Okay, so in which case the set of states, capital S, might be a set with different descriptions. So it might say it's raining, or it might say it's sunny, and so on. Okay, so that would be something that I will find out eventually. Or it might be, I might be interested in the roll of a dice, so we'll use that example a lot. What are the different possibilities? On a 6-sided dice, there are 6 different relevant descriptions. As soon as I know the number on the dice, the face-up number, then the uncertainty is over. Okay? So the state space would be all the different states, 1, 2, 3, 4, 5, and 6. I don't know what the number is before I roll the dice. Okay, it's one of these numbers. And then when we roll the dice, we might talk about the true state. Okay, so we might say the true state, or we might say the state that obtains, or the state that happens. Okay, and I'm sure there's other descriptions. Okay, so that's the basic idea. To describe uncertainty, we have some set. This is a primitive of our model. It's given to us, or we have to construct it when we're making decisions. And this set of states lists all the possible relevant descriptions of the world being what we're interested in for our decision making. If we don't know the state of the world currently, then there is uncertainty. If we know the state, there is no uncertainty. Okay? So these were both dealing with something that will happen in the future. We're not going to model time explicitly in this case, but this could also refer to something in the past. So, for example, A current line of research, which is very important, is tracing the origins of the coronavirus. And there's various possibilities of where this virus started. The most likely seems to be that it started in bats and transferred to humans, but there are other possibilities, and of course, possibilities, I guess, which many haven't considered yet. Of course, this would have happened in the past, so you could imagine that the state has already been decided. In some sense, there is a true starting point, but we might never find this out. So there remains uncertainty. Okay, so that's just an example to say that where in some case we're thinking of something that will happen in the future, but there are certainly uncertain things that will remain uncertain, possibly forever. Okay, now in our case, we're going to talk about the state occurring or discuss what happens when we find out the true state and so on. So we'll typically think of things that we can find out, okay? Or we'll describe the information that we're able to find out. So we might not be able to find out the true state, but we'll be able to describe what information we can know once the true state has been decided, okay? Which basically means we'll be able to rule out some things, but maybe not everything. Okay, so this is the mathematical framework, really, for studying uncertainty. It's very simple. It's just an abstract set with states in it that we interpret as descriptions of the world, leaving no uncertainty. One idea that we'll use is something called events. Okay, so what is an event? Now, formally, it is a subset. So events are subsets of the set of states. Okay, so I might, for instance, call a subset A, which could be, if I look at our rolling the dice example, it could be the subset which contains the numbers 1, 3, and 5, the odd numbers. And then I could talk about the event that the number is odd happening, or the event that the number is odd obtaining, by which I mean the true state is either 1, 3, or 5, in which case we say that event has happened. Okay? Now, the set of all events we'll just denote this as omega. Okay, capital omega. What would this be? Well, if we have a finite set like this, then it might be the set of all subsets, okay? Typically, the set of all subsets is denoted either like this, so 2 to the power s, because this is how many, if we have a finite set, this is how many subsets, different subsets, can be constructed from that set. Okay, so if we have a set with just 2 elements, rainy and sunny, we can construct 4 subsets. So an empty set, rain by itself, sun by itself, or both of them together. That would be 4 different subsets. Okay, and in general, there are 2 to the power s. So sometimes we would just write omega is equal to 2 to the power s. In some books, they do a kind of fancy curly p like this to mean the power set. So this means the power set of S, which is the set of all subsets of S. Okay, but we'll just denote it omega without saying too much about it, apart from that we can do some basic operations like if we have 2 events that belong to this omega, we can take intersections, we can take unions, we can take complements and do all of the sensible set theoretic algebra that we've seen before. Okay, so that's what we mean by uncertainty, states of the world. Once we know the state, there is no uncertainty. Uncertainty exists because we don't know the state, and we can talk about events as different subsets of the state space. To model uncertainty in microeconomics, we use a state space, and we already gave the example of rolling a dice. Often it's useful to produce diagrams of this state space. So this is how we're going to do it in our lectures. We're going to represent the state space as, here I've just drawn a rectangle, and inside this rectangle I've drawn 6 nodes or little circles, and you can see here there is a a node with a number 1 attached to it. So that is the state that the dice has been rolled and the number was 1. And we've also got 2, 3, 4, 5, and 6. Okay, so this would be a finite or a discrete state space. We can see the individual states. If I was talking about a continuous state space, I could just represent it as a rectangle or a line and just allow every single point in that space to be a particular state. So that will happen later as we talk about uniform distributions. In lecture 3 in particular, they will become important. We'll imagine the state space being a line and every value along that line represents a different state. Here we're just working with a discrete state space today, or a finite state space, more specifically with 6 states. Now that we've drawn this state space, we can identify events. So if we remember, an event is a subset of the set of states. Okay, so in particular, an event might be the event that the number is odd. Okay, now how would we represent this event? It's going to be a subset of the set of states. Here I've labeled it capital A is equal to a set, so I'm using curly brackets, with the states 1, 3, and 5 in it. Okay, so that's the subset of all of the numbers which are odd, and I can represent this diagrammatically by just drawing a shape around these states and labeling that event as A. If the event, the number is odd, happens, then all we're saying is that when the dice is rolled, the true state is either 1, 3, or 5, so it belongs to that event. Now that we've introduced how we model uncertainty in microeconomics, let's talk about information structures and how we'll describe these using the tools we've developed so far. To do this, we're first going to need a mathematical idea called a partition. So let's go on paper and develop the necessary mathematical tool before we talk about information structures. Okay, so to formally model information using something called information structures, we're going to use a mathematical tool called a partition. Okay, now you may have a intuitive sense of what this means. Essentially, it means to take a set and chop it into pieces. Okay, now how can we make this formal? Well, let's develop our intuition. If we're going to take a set and chop it into pieces, the first thing we want is that each of the pieces has something in it. Okay, the second thing is that the pieces are separate. Okay, so we are actually chopping the state space. And the final thing is that if we put all the pieces back together, then we get back to our set of states. Okay, so we're not throwing anything away. So how can we define this formally? So as a definition of a partition. So a partition of any set really, but we'll say of the set of states S, a partition of the set of states S is, well, it's going to be a collection of subsets, but we know they're called events. So it's a collection of events, subsets of the set of states. What's it going to look like? It's going to be a set. So I should say a set of events or a collection of events. A1 to, well, how many are there? Let's just introduce some arbitrary number k. So there are k different elements in this partition such that, and now we want to write some simple rules. So this is what we'd call an axiomatic definition. So there's lots of different collections of events, and any of those that satisfy the following rules, we're going to call them a partition. So the first rule is that each piece has something in it. So how could we write this? We could write AI is not equal to the empty set, okay, for all I equals to 1 all the way through k. Okay? So that's one way of saying every piece has something in it. There's no empty pieces. The second condition is that these are separate pieces. We're chopping up the state space. How would we say that? Essentially, there's no overlap between any of the pieces. So if I take AI and I intersect it with AJ, okay, two different elements from this partition, then this should equal the empty set. There shouldn't be any element in common. So when would this occur? Well, as long as I is not equal to j. Okay, so for all I not equal to j, obviously taking I and j from the numbers 1 up to k. Okay, so the first condition, all of the pieces have something in them. The second condition is that the pieces don't overlap. And the third condition was the idea, well, we didn't throw anything away. So if we take all the pieces and add them back together, so if I take A1 and consider the union with A2 and A3, and I'm just continuing this, I'm taking the union, combining all of these sets back together, all the way up to AK, then this should equal precisely the set that I started with, which in our case was the set of states S. Okay? So this is a purely mathematical definition that captures the idea of a partition. There are lots of different partitions. There's loads of different ways of chopping up a cake. But if we look at any collection of events that satisfy these three rules, then it's okay to call that collection of events a partition. Now that we've introduced the idea of a partition formally and we know precisely what this concept is, we're ready to talk about what we mean by an information structure. The simplest definition is this: an information structure is a partition of the state space. Okay, so an information structure is going to take the state space and chop it into pieces. Each piece is non-empty, the pieces don't overlap, and if we add all the pieces back together, we get the state space. What does this mean, though? How do we interpret the idea of these information structures? Well, if we're given an information structure, like I've labelled here, a partition, which is a set that contains these subsets A1 all the way up to AK. Now, each of these are called information sets. So this decision maker has k different information sets, and those information sets constitute a partition of the state space. What do these information sets mean? Is the following: suppose the true state of the world is little s. Okay, so there is a true state of the world. Our decision maker might not know the true state of the world, however, but it must be the case, because this information structure is a partition, it's chopped up the state space. So this state has to be in one of these information sets. And this is what the decision maker knows. Okay, so when the true state of the world S, there is some, let's label it capital A subscript I. So there is some information set AI, and that state S belongs to that information set. Well, then the decision maker knows that only that event AI has obtained. He doesn't know any more than this, or indeed any less. Okay, so whatever the state of the world is, the decision maker might not know it, but they do know the information set that contains the true state. Okay, so they're able to rule out an awful lot of things. Let's look at some examples to see how this works. So here is a simple example where I've labeled this high or low, and in this case the decision maker has an information structure which is a set containing two subsets, A1 and A2. The first of these, A1, contains low numbers, so it's a set with just the numbers 1, 2, 3 in it, and the second information set in the information structure, labelled A2, the pink set, has 4, 5 and 6, which are the high numbers. Okay? So intuitively, when the dice is rolled, one of these 6 numbers will be the true state. The decision maker won't know the true number, however, but they will know whether that number is high or whether it's low. Okay? So if, for instance, the true state was equal to 2, then the decision maker knows that event A1 has happened. And that's all they know. They know that A2 has not happened. So they can rule out 4, 5, and 6, but they can't rule out 1 and 3. So one way of thinking about this, here I've taken a picture of a dice. So just think of this as one dice, and I'm showing it from 2 different sides. You can see the high numbers 4, 5, and 6, and from another angle, the low numbers 1, 2, and 3. Now imagine I place a sticker on each of these numbers in such a way as to represent this decision maker's information. So I've put a pink sticker on each of the high numbers and a blue sticker on each of the low numbers. Okay? Now, if the decision maker rolls this dice, clearly they can only observe the outcome is blue or pink, high or low. Okay? So that's a simple way of thinking about this idea of an information structure and how we interpret information sets. Any state that is inside the same information set looks exactly the same to this decision maker. Here is another example of a different information structure. So in this case, I've labeled this odd or even. This is essentially what this information structure will capture. So if I let the individual B's information structure be a partition with elements B1 and B2, and the first information set B1 contains the numbers 1, 3, and 5, so the odd numbers, and the second information set B2 contains the numbers 2, 4, and 6 within B2, then this information structure is essentially putting blue stickers over the odd numbers and pink stickers over the even numbers. So when we roll that dice, this decision maker only knows whether the outcome is odd or even. They cannot distinguish between 1 and 3 and 5. They look the same to this decision maker. But if they see a blue outcome, they can rule out the pink numbers. Okay? Now, one thing I should point out here is that when we draw information sets in these diagrams, I've drawn dotted lines around 1, 3, and 5, blue dotted lines around those to represent information set B1, and pink dotted lines around 2, 4, and 6 to represent B2. Now, this isn't always done, but it's good practice in general to use dotted lines to represent information sets. It's very, very common. You won't see it in all textbooks, but maybe you'll see it a lot in game theory books where different decision nodes are grouped by the same information set and they will draw dotted lines around them. So you will see it quite frequently. Let's give some other examples. So in this case, I've represented both mathematically and graphically what we mean by perfect information in this case. Okay, so perfect information would mean whatever the true state of the world happens to be, I know what the true state is. So we could imagine a partition which contains six information sets, and each of those information sets just contains one element. So C1, C2, C3, C4, C5, and C6 just contain the numbers 1, 2, 3, 4, 5, and 6 separately. So every state is in a unique information set. Clearly, in this case, if I roll the dice and the outcome is 3, the decision maker knows that information set C3, that's the event that has obtained, and there's only one element in that set, so they know the dice is number 3. Okay, so this is how we would represent perfect information, every state being on its own in an individual information set. What about the other extreme? Void information is essentially, well, you could think of this as useless information or completely lacking information. If I take a dice and put blue stickers over every single number, then rolling the dice really doesn't tell me anything at all. Okay, so how would we represent this? We would just put all of the states 1, 2, 3, 4, 5, and 6 into the same information set, which here I've labeled as D1. And of course, in this case, whatever the outcome, the only thing I can say is, well, something happened, but I have no way of ruling anything out. All of the states look identical to this decision maker. So it's kind of the most useless case. Also, as a sanity check, we should think that when we develop a theory of how we value information, then we should be thinking, well, perfect information should be the most valuable and void information should be worthless. Okay, so these are things to keep in mind in later lectures as we develop the theory of valuing information.